Inside any major industrial facility, the sheer scale of chemical storage and warehousing presents an immediate, compounding physical risk. Thousands of tons of materials are stacked, piped, and contained within finite architectural boundaries. To manage this space, the initial instinct is to rely on standard geometric volume. You measure the length, multiply by the width, and multiply by the height. Relying on this pure geometric volume creates a lethal trap for engineers. A steel process tank mathematically holds exactly 10,000 gallons, but filling it to that absolute limit removes the physical margin for thermal expansion, resulting in a ruptured vessel. In safety engineering, capacity calculations serve as rigid risk control mechanisms. They allow professionals to anticipate physical and chemical behaviors before they compromise a structure. This is the master storage equation. It overrides raw geometry by integrating operational realities, inevitable spatial losses, and strict safety limits into a single, actionable metric. To accurately deploy this equation, we must build it layer by layer. Start with the baseline geometry, identify traps in unit conversions, apply real-world utilization rates, and translate volume into load constraints. Mapping theoretical space against physical load limits provides a definitive defense against structural and chemical failures. Every storage capacity calculation begins by isolating the physical environment and identifying the correct geometric shape. This diagram illustrates our two most common environments. For a rectangular warehouse, the baseline volume equation is straightforward: length times width times height. For a cylindrical process tank, we calculate the area of the circular base and multiply it by the height. Look closely at this result. We have identified the volume in cubic feet, but the Occupational Safety and Health Administration strictly enforces flammable storage limits in gallons. This unit mismatch is a major point of mathematical failure in safety risk assessments. Standard mathematical formulas yield spatial measurements, cubic feet or cubic meters. Federal regulatory caps, spill containment requirements, and pump flow rates are almost universally dictated in liquid volume, gallons or liters. To bridge this gap, you must commit the imperial conversion constant to memory. 1 cubic foot is equal to exactly 7.48 gallons. For metric environments, the constant is equally rigid. 1 cubic meter contains exactly 1,000 liters. Converting dimensions to match regulatory units before executing the final risk calculation is the only reliable way to avoid severe compliance failures. Moving inside the facility, this floor plan shows the total area footprint, but total area is deceptive. We must map out the emergency exits, fire panels, and structural columns. By mathematically deducting these non-usable spaces from the total area, we find the net area. Multiplying this net area by the available ceiling height yields the raw volume of the room. This raw volume is practically unsafe. In a functional warehouse, forklifts require wide aisles, and personnel need clear access routes to navigate safely. We account for this operational reality by introducing the utilization factor. This is a mandatory decimal multiplier, typically ranging from 0.7 to 0.9, depending on the shelving configuration. Applying a 0.8 utilization factor immediately reduces our raw volume by 20%. This smaller, denser block represents our true effective capacity. Mathematically overestimating warehouse space by ignoring this factor directly causes blocked emergency exits and increases in the building's fire load. Outside in the tank farm, we face a different set of physical deductions. This schematic shows a vessel's geometric capacity, but the internal space is occupied by process hardware, pipes, heating coils, and agitators. To find the true net capacity, we apply a specific sequence of subtractions. First, we subtract the deadwood, the volume physically displaced by the internal hardware. Next, we subtract the heel. This is the residual, unpumpable liquid resting at the very bottom of the tank below the lowest suction line. With the physical hardware and residual fluid accounted for, we must apply the most critical process safety variable, the fill percentage constraint. Process tanks are subjected to temperature swings. As ambient heat increases, the liquid inside absorbs that energy and physically expands. We are required to leave an empty vapor space at the top of the vessel. This thermal expansion margin accommodates the swelling liquid without putting hydrostatic pressure on the steel roof. Failing to calculate and enforce this margin removes the expansion space. The expanding liquid will pressurize the rigid container, directly risking a catastrophic vessel rupture and a boiling liquid expanding vapor explosion. We must shift our perspective away from the interior of the containers and examine the physical supports bearing their weight. Storage capacity represents a severe structural load risk. The weight of the material dictates the integrity of the facility's supports. A facility might have the spatial volume to hold thousands of gallons, but we must convert that spatial volume into a downward physical weight, measured in pounds. To execute this conversion, we use specific gravity. This is the exact ratio of a chemical's density compared to the baseline density of pure water. Pure water has a specific gravity of 1. It weighs 8.34 pounds per gallon, or 62.4 pounds per cubic foot. This diagram shows the total load calculation in action: volume in gallons multiplied by 8.34 multiplied by the specific gravity. Both drums take up the exact same physical space, but the chemical drum has a specific gravity of 3.5, meaning it exerts 3.5 times the downward force. Identical volumes of different fluids generate vastly different force vectors. This force is measured against the facility's pounds per square foot limit, the structural threshold that cannot be exceeded. Calculating volume without applying specific gravity mathematically guarantees that you will exceed those limits, resulting in rack failure or total floor collapse. If structural limits fail and a primary tank ruptures, we rely on secondary containment. A containment berm is the ultimate environmental failsafe, designed to capture the entire volume of a catastrophic spill before it reaches the facility grounds. The required volume of the berm is calculated using our baseline geometry: length times width times height. However, this geometry is governed by a mandatory regulatory constraint, the 110th. This extra capacity is an operational necessity, accommodating heavy precipitation from storms and the massive influx of fire suppression foam during an emergency response. Accurately calculating this final 10% buffer dictates whether a localized spill is safely managed or whether it overtops the wall and escalates into a major federal environmental incident. Looking at the facility as a whole, the scale of the responsibility becomes clear. Pure standalone geometry is an inadequate tool. It provides a theoretical maximum that simply does not exist in the physical world. We return to the master equation. Safe capacity is geometric volume minus losses times utilization times safety limits. We account for physical losses by deducting internal deadwood hardware and unpumpable heel fluid. We satisfy utilization by acknowledging wide aisles and emergency exits. And we enforce the safety limits by mapping structural load limits against specific gravity and ensuring our containment berms meet the 110% rule. For safety professionals, and specifically for the ASP exam, mathematics must be treated as a rigorous compliance decision tool. Finding a theoretical value is just the first step. The true value lies in executing flawless unit conversions, modeling structural loads, enforcing thermal margins, and using data to prevent disaster.